to RF filter design. So today we will focus more on the step impedance filter design. So what is step impedance filter design? So we start with the, okay, so I will share the slide or presentation from the iPad. Okay, before we go any further on the step impedance design, so basically we have learned about the filter design, especially using the lump element, which is using the RLC, inductor, capacitor, and resistor. So using the lump in components such as SMT, so normally it can go up to 5 to 6 years, but in microwave design, we might use for more than that frequency. So we need to using basically two other methods, which is using the step impedance or step filter design or step impedance techniques. So basically, the derivation, or in order to get the step impedance filter design, we use the T network using the ABCD matrix. And from that, we got the Z11, Z12, Z22, and Z12. And from the derivation and from the microwave filter section in microwave engineering book, so basically, finally, so after some derivation, so I'm not showing that. So X2 is equivalent to Z0 BL over 2, and we got X equivalent to Z0 beta L. And here we can see that with a simple or short transmission line, it actually can be converted to the inductor, which is XL equivalent to ZH beta L. And in this case, you can see that in this case, Z0 is very high. So we are using the high impedance. And for the case of transmission with short transmission, okay, so here we can see that DC is equivalent to JY1 beta L to power of minus 1. So here, so actually, it's representing a shunt capacitance. So in this case, we are using the Z0 is very small. So the use of this relatively short high impedance and low impedance section of transmission lines is the origin of the alternate name for the step impedance filter, which are using the high Z and low Z filters. Okay, so we can remember here that for a large impedance, we are using inductor. And for the low impedance, we are using the capacitor. Okay. So that's why come up with a formula in order to calculate the electrical length. So why is not showing? Why is not showing? Okay. So here we got the formula in order to calculate the electrical length. So here we can represent, in order to get the capacitor, we can have a beta L is equivalent to CZL over R0. While for case of inductor, so why is not showing here? Okay. So we have the beta L represent equivalent to LR0 divided by Z height. Okay, from here we can get the electrical length. Okay, in order to understand the design of step impedance filter design, let's look on a example here. So the example is taken from the microwave book. Design a step impedance low pass filter having a maximally flat response of a cutoff frequency of 2.5 gigahertz. So it required 20 dB insertion loss at 4 gigahertz. The filter impedance is 50 ohm, and the highest practical line is 120 ohm, and the lowest is 20 ohm. Considering the effect of losses when the filter is implemented with microstrip substrate having D equivalent to blah blah blah, permittivity, tangent loss, and copper conductor. So design your filter. So as usual, in order to to solve the problem, so basically we need to, the first step taken is we need to determine the number of order of the filter. So n equivalent to what is n. So we have learned from the previous videos, there are two ways in order to get the n. So either we use the formula or we use the graph. So if we want to use the graph, for example, we calculate that omega over omega c minus 1. So there's so we got 0.6, and from the table, so maybe from the table, so at attenuation of 20 dB, so here we get that n equivalent to 5 somethings, and the best we can choose is n equivalent to 6. Second step, as usual, is the same procedure as before. We need to draw the normalized prototype circuit. Normalized prototype circuit. Don't forget this step. So after you have determined the number of order, so you draw the prototype circuit. So in this case, you use the capacitor first and following the inductor for this low pass filter. And you just take out the value from the table. So whether you want to calculate it, you can also calculate, or you can directly taken from the table. So here you determine the G1 until G6, and you determine that so it is equivalent to C1. Okay, next step. So next step, you need to calculate uh, the equivalent line or the electrical line, which is representing the beta L. So either by beta L is using for inductor or capacitor using the above formula. Okay, so in order to do this, it's better for you to draw a table. Okay, so a table need to be drawn. So here is an example of the table. So you write a section. So section here 1 to 6, and you include the alternate impedance, whether it's Z low or Z high. So in this case, we choose capacitor first. So capacitor are using the Z low first. Okay. So you are using capacitor, inductor, capacitor, inductor, capacitor, and inductor. So you include this impedance value. So next, you put the table for beta L. So beta L here, you can calculate using the formula above. So let's say for the capacitor. So beta L is equivalent to CZL over R0. And C for the the first value is 0.571 times Zn, and this time is using the low 20 ohm, and over R0, which is the 50 ohm. And here you will get a value. So this value is not yet, it is in radian. So you need to convert from radian to degree. So how you want to change it? Maybe you need to multiply with 180 degree divided by pi. Okay, in order to convert it into a degree. So you do all the calculation for the next, the second order, third, fourth, fifth, and sixth sections, and you will get all the formula here. So next step, so you have determined the Z impedance and the electrical line in degree. So now what you want to do is to calculate the width and length of the transmission line, okay, or the microstrip layout. How do you want to do that? Okay, there are a few ways. So we can, if you are designing it, you can use the line calculator from the EM. Okay, so this example was taken from emtalk.com. So you can include your the constant. For this case is 4.2. Example, the thickness. So in this case, 0.5 ml milliliter, and you are designing at 2.5 gigahertz. Okay. Include the, just now you have the 20 ohm, okay, with the electrical length of 11.8. So here from this, you can just push the button for synthesize, and you got the value of width and length directly from this line calculator, and you can get that okay, it's around for the width is around 9. What is the oh, okay, sorry, the value is should be in mil. Given the unit is in mil. Okay, let's see, we compare with the book. Is the value is quite far away. Tangent loss. Oh, sorry, it's my mistake. Let's see, it should be 0.1. No, it should be, actually we're having D equivalent to 0.158 cm. So this means 1.58 mm, right? Okay, all right, we compare from the book here. So here, from this line calculation, we get the value of width is around 11.27 mm and the length of 2.08 mm. So if we are looking at the book here, okay, so the value just now is around 11.27 7 mm for the first section, and the length is around so it's approximately 2.05 mm. So that's from the calculator. But unfortunately, in final exam, so you won't able to use that. Okay. So in order to design that, so we need to use the formula. Okay. So how you want to find W from the formula? So here is the formula given. Whether you want to use W over H is less than 1 or W over H is less than more than 1. So in this case, you assuming W is over H is equivalent to 1. So this value Z0 is given. What is that? So ZF is also given. EEFF you also need you can find from here. So H, the height of the substrate, so is given. So you just include all the formula. So you can calculate the W here. Or or you can use the table. If the final exam is given the table, so you need to interpolate the table. So in this case, the impedance givens are 50. So 10, 20, 30, 40, 50. Okay, so let me draw from this table. 10, 20, 30, 40, 50, 50. And permittivity is around what? So around 4.2. So around 4.2, so it will be around here. Okay, so this is just approximation. So in this case, you have the ratio of W over H is around 1.8. So this approximation, and you know the height of D is 0. The height of the substrate is 0.158 centimeter. So H is 0.158 centimeter. So W1 is 1.8 times 0.158 centimeter. So I think you will get around okay. So maybe the approximation is not good. Okay, here you will get around 1.8 times. So you get W is around 0.3 cm. So it's far away from the never mind. So this is just one way in order to determine the W. So using the formula or using the table. So this may be asked during the final exam. So next, so how do you want to find L? So you already know that, okay, from the basic lambda. So lambda G is equivalent to lambda not okay. So the basic one, we have the lambda G over 4 is representing the 90 degree of electrical length. So if you have calculated the electrical length for the first section is 11.8 degree. So from here, you can determine L1 is equivalent to 11.8 degree times lambda G over 4 divided by 90 degree. Okay. So here you can calculate all the value. So you know that lambda is equivalent to C over F. And lambda naught is equivalent to C over F square root of E up. So here, so the speed of light, the frequency of operation, and the permittivity. So in this case is 4.2. And here, so you can estimate the electrical length of the mentioned section. So here, for the first section of this step impedance filter, so you can have a, so this for the section of, we have the W1 and H1, which representing the capacitor. And here, so you keep on counting for the others impedance for inductor, capacitor, inductor, and we able to draw the microstrip layout. So here is the microstrip layout, which is representing the section number 1, section number 2, section number 3, section number 4, 5, and 6. And both of the input and output of the filter must be connected with the terminated load, which is normally we are using the 50 ohm terminator, which is this case is Z0. So for each of the elements, so you need to determine the width and length. So that's why you are calculating all the value in this table, which is you can label this. So this is the L1 with the width of W1, L2 with the width of W2, and so on. You label it from this layout. And don't forget also when you design, you still need to determine the width of the input and output impedance, width and length. So this can be, again, the width you can calculate it using the formula, or you can get it from the table. While the length, so it's easy, just the interpolation at 90 degree representing the lambda g over 4. Okay. So you can see from the layout, this is the alternating the impedance from the Z low, Z high, Z low, Z high, Z low, and Z high for the 6th section. And you can see that when you are using the Z low, the low impedance, the size of the layout is big. But okay, the blue one, the size of the layout is big. But when you're using the Z high, the size of the layout will be small. So especially, it is actually mentioning the width. Okay, high impedance will have a small width. Low impedance representing the high width. So normally in designing a filter using the step impedance, so as a designer, we choose so not so high impedance Because if you are using the very high impedance, your width will be very small and it will be difficult to fabricate. And if you are using the very low impedance, so the width will be very big. So you need to choose the best in high impedance or low impedance. So you can see that this is the graph of comparison between the step impedance and lump element. Okay, lump element. So you can see that lump element give better performance, especially in you looking at the sharper cutoff frequency compared to the step impedance. However, okay, you know already the problem of lump element where the capacitor and inductor value, which is if it's for example 2.576 picofarad for capacitor, so the exact value will be difficult to find and to fabricate it. So if you want to have the exact value, so it will be very expensive. So that's the problem of the lump element. However, when using the step impedance, okay, so for a certain application is acceptable with with this kind of cutoff frequency, which is less sharp, is okay. So yeah, it's okay to use this step impedance filter design. Okay, so maybe if we want to have so in this case, the step impedance filter element depart significantly from lump element value, and we can see that the attenuation is higher compared to the lump element. And maybe if you want to have a more accurate design of filter, you can choose with using the higher higher end. So this design is using n equivalent to 6. So perhaps you want to have a lower attenuation, so you can choose n equal to 8, 10, and so on. But when you increase the number of elements, so you got a better performance. Unfortunately, you will increase the complexity and will increase the cost. So that's all. So this video today is just for the example of designing the step impedance filter. So see you in the other design.